All right, so we've talked about radiation between surfaces that behave as black bodies and enclosures, and now we're going to extend that to surfaces that are not black bodies. So let's take a look at figure 13.9 in your book. We see an enclosure in the top part of that figure. The surface is, at the bottom has irradiation onto the surface and radiosity coming from the surface. So the net radiation coming from the surface, Qi, can be expressed as the radiation coming from the radiosity minus the radiation coming to the surface, which is the irradiation. We can relate that to the definition for radiosity, which is the emitted plus the reflected radiation. And I could put that reflected radiation in terms of reflectivity and the irradiation terms. And finally, I could put those two things in terms of the absorptivity. And I have the net heat transfer rate in terms of emissivity and absorptivity. Now let's introduce the concept of a gray surface. So radiation is a complex phenomenon. Properties might be dependent on the wavelength or the direction of radiation. And we often make a simplification and model surfaces as gray surfaces. So a gray surface is independent of wavelength, or the properties of a gray surface are independent of wavelength over the spectral regions, i.e. the wavelengths of radiation that's being irradiated onto the surface and emitted by the surface. Furthermore, Kirchhoff's law, which your book talks about in chapter 12.6, states that for any surface within an enclosure that the emissivity and the absorptivity are equal to one another at a given wavelength and angle. And since for a gray surface, its emissivity and absorptivity are taken to be independent of those two things, then for a gray surface we could say that the absorptivity and the emissivity are both equal to one another. So we add this to our equation for Q net due to the radiation from the surface, and then we add our definition for a black body, and then we take a step back and get things in terms of radiosity and rearrange to solve for J. We could also solve for that radiation in terms of radiosity. And then we can plug that definition into irradiation in terms of our original equation. And then we can move things around to get things in this form. So why would we do that? Well, because now it looks a little bit like Ohm's law. We have this driving force for the heat transfer at the top and the resistance to radiation from the surface at the denominator. And that resistance is called the surface resistance. And now we can think of things in terms of thermal circuits. So on the right here, we see how that thermal circuit would look. The direction of that net radiative heat transfer depends on how large Ji is, the radiosity, and how large Eb is, the emissive power of a black body at the temperature, that surface temperature. It'll be from the surface if the emissive power of that black body at the surface temperature is larger. Furthermore, we can see that the surface resistance is 0 for a black body, and in that case, EBI and Ji are equal to one another. And now let's finally look at the radiation exchange between surfaces. So remember the expression for two black bodies exchanging radiation. Well, the equation for two diffuse gray bodies looks really similar, and it makes intuitive sense. So on the right, you have emitted radiation leaving a black surface and irradiating from another black surface. There's no reflection for the black body. But on the left, we've accounted for that reflection term in terms of radiosity. And if we know the surface temperature and we can calculate EB, well, that first equation is very helpful in defining Q. But if we don't know the surface temperature, that other equation is more helpful, the one that's in terms of the V factors. So here's the thermal circuit showing the radiation exchange between two surfaces in an enclosure. We could see the first term is the surface resistance, surface radiative resistance. But what about the other term? So let's back up just a second and look at the second equation. Or look at the equation for Q. We have this we have the radiosity, which is the emitted minus the reflected term, and the irradiation term. Remember, if we had a black body, that reflected radiation is 0, so the resistance R1 could be thought of as the resistance to black body emission, and that only deals with the surface of interest, not the surrounding surfaces. But we also have to have the effect due to the interaction with other surfaces, and that deals with orientation, i.e. our view factors. And that resistance is sometimes referred to as the space or the geometrical resistance, so we can define Q in terms of those things as well. Alrighty, so we'll work some problems with this the next time. Let me know if you have questions, and thank you for watching.